All right. So you don't have any more homework assignments in this class, but you do have 2 design projects, and those are just like homework assignments on steroids, so to speak. They count for a fair amount of your grade. I think they're 10% each, if I'm just double checking to make sure. To emphasize the importance of these, let's check the syllabus. So design project number 1 is due a week from today at 11:59 p.m. And sure enough, it's worth 10% of your grade. So design project 1 and 2, which is the last 2 things that you got in this class, collectively account for as much as all of the previous assignments combined. The good news is I don't think that you should feel intimidated like that that design project is like inordinately difficult, because it's not. The reason why it is kind of separate and standing alone from the other assignments is that it's kind of synthesizing and bringing together multiple concepts. And so here's the design project. There's 3 components to it. The first is I ask you to analyze a watershed and then design a flume, a partial flume that could be used to determine the flow rate at that watershed. And so to design the flume, you have to know how big the flow it's likely to encounter is. And so on the design project, what I ask you to do is use NSS for this first watershed, National Streamflow Statistics, to determine what's the likely runoff for the 2-year storm. So that's easy enough for you to do once you find the location. Find the Q2, and then based on the data that you've seen before, these empirical equations and the range over which they typically apply and the submergence criteria, design a flume that won't submerge, that can accommodate that 2-year flow. And then in part B of that first part of the assignment, then determine what would be the flow rate if the depth at A was less than half the depth that you've determined when you were deciding how deep the water would be when your Q is the 2-year flow. So basically what you're going to be doing, ordinarily a partial flume is used to determine Q for a given H measurement. We're flipping that on its end, because what you're doing is you're trying to decide how big the flume needs to be to accommodate the flow out of this watershed. So Q will be known when you're designing it, and you're selecting an appropriate width that ensures that it's not submerged. So the submergence criteria is maximum H sub B to HA is given here. So that is the first part of the design project, is just applying some flume calculations and combining it with watershed analysis. Then the second 2 parts of the design project is related to culverts and HY8. So that's what we're going to start on today. Is I ask you in part 2 to analyze a culvert that I've described, and then in part 3 to design a culvert. And so after today's class, it's likely that you'll be able to start on part 2 of the design project. And I think you could already complete part 1 of the design project just based on the simple example calculations that we did last week for partial flumes, and based on what you already know how to do in WMS for watershed modeling. So you can already start working on part 1 of this design assignment. Part 2 you can finish probably after today, and then we're going to do some more examples in class on Wednesday related to HY8 and culvert design. So that's the entirety of this design project 1, which is due a week from today. We'll talk more about it in class on Wednesday, but I wanted to point that out, that it's due by 11:59 p.m. on Monday, a week from today. And then next Monday is when we're going to have an online class, because that's the day of the eclipse, and I'm not going to be here. Maybe some of you will be also on the road trying to experience it. But any schedule or announcement related questions before we get into HY8? All right. So this is where we left off Friday last week. We were just talking about some of the different inlet possibilities, and typically the purpose of having anything other than a projected barrel is just to guide the flow into the pipe and reduce energy loss along the way. So the projecting barrel is the orientation that has the least flow capacity of all the culvert options. And so when you're doing your design, if you're not able to convey enough flow through the culvert, then you can add an end section, a miter, wing walls, head wall configurations that maybe will increase the capacity 5 to 15% typically. Culverts are important because if they're sized wrong, this is a view of a culvert where water was flowing under a roadway, but the culvert wasn't large enough. And so what was happening is there was a lot of pooling upstream of the culvert. Just to give you a side view, here's the ground, and then here was a road. And what they had was a lot of soil that they basically barreled through with a culvert. And so here's this circular culvert opening. And if the pipe is too small, what happens is that the water level rises really high upstream. And when the water level is rising like that, then it can not only flow through the culvert itself, but it seeps through the soil on the outside of the culvert. You know, like around the bedding that was under the culvert and the fill that went on top of the culvert. And so if there's too much headwater, which is the case here, then it starts to wash some of the soil out. Like some of the really fine soil gets rinsed out as the water's seeping through. It carries the sediment with it, and it goes through this process where if the fine soil gets washed out, then it makes the voids larger, then the water velocity can increase, and there's further energy going through there that can carry larger particle sizes. And it's kind of a progressive thing where eventually you've got water seeping at a higher velocity, which carries more soil, and it can cause a structural collapse, which is what happened here. The water carried some soil, enough of it that when the flow rates were high, then the entire road got demolished, the culvert floated away, and this is going to obviously take a little bit of time for them to repair. So that's kind of the stakes, is that if you have overtopping and you're not prepared for it, or if you have high headwaters and you're not prepared for it, then it can be pretty destructive and costly. So in the background of the calculations that HY8 is doing is it's assessing what controls the flow rate and what limits how much Q gets through the pipe. And there's two main categories of what controls how much water is flowing through the pipe. Inlet control is associated with high slopes and supercritical conditions inside of the culvert, or it's associated with openings that are the limiting factor of how much water can flow through the pipe. So if the pipe is really steep, then it has plenty of capacity, but just the water sometimes can't get into the pipe at a fast enough rate. You maybe remember the orifice equation, which says if you've got like a tank of water and a hole in the tank, then the rate that the water is coming out is related to Q equals A square root of 2GH, where H is the height of the water from the water surface down to the center line of the orifice. So if the water is pooling really high above this opening in the culvert, then you're basically doing the orifice equation to find out how quickly the water can get through there. So inlet controlled just is associated with maybe you've got a tall headwater and water can't get into the pipe at the same rate that the pipe is carrying the flow. Or sometimes there may be a hydraulic jump inside of the culvert if the tailwater is high. Like if the channel downstream of the culvert doesn't have much capacity and it's pooling downstream, then that could force a hydraulic jump to form. Or it could just be that the supercritical flow remains supercritical. All of these are illustrations of inlet control. And back in the bad old days before HY8, it was a pretty laborious process to determine which different kind of inlet control you had and what the capacity through the culvert was going to be. There are these pretty sophisticated and complicated nomographs where you'd do a graphical solution that the manufacturers of culverts would come up with these. It's almost like a slide rule, if you've ever heard of a slide rule before. This process of drawing lines that intercepted the diameter of the culvert, the flow rate, and then the likely headwater depth. Here's an illustration of a nomograph where you would find your solution by intersecting the diameter of the pipe with the flow rate, and it would go sideways and intersect these different lines that told you what the headwater depth is. So outlet control, you can see now that it's not as steep as it was in the case of inlet control. It's associated with subcritical flow through the pipe, so shallower slopes, or it can be that the pipe is full because both the headwater and the tailwater is submerged, or just that the capacity through the pipe is insufficient to have a free flow. So HY8 takes the burden off of us from determining whether it's inlet or outlet control, and it kind of automatically applies the equation that appropriately limits the flow. And so it'll look at the least capacity that can be accommodated and then substitute in that flow equation automatically. So culverts can be sometimes very rudimentary, just like a pipe sticking out from under a road. And sometimes they can be very expensive and costly because they expect really high flash flood velocities to come through. And so this is a picture that I took over in the United Arab Emirates when I was living there of some culverts that they have in the desert where the mountains are so steep and rocky that when it rains, all of the water runs off very quickly. There's very little vegetation to slow down the movement of the water. And so because it concentrates so quickly and with such a high velocity, they have to have these enormous culverts to pass the flow under the roadways. And you can see that they've got all of this rock, which is armoring both the upstream and the downstream side of the culvert. And not only is it's rock, but also they have a wire mesh holding the rock in place because they're just expecting quite a lot of scour and don't want to build this again a second time. So to give you an idea of the size of it, that's me, and so it's twice the size of me, and you'd normally think that a desert area wouldn't get much rain, and they don't. They only get about 4 inches per year of rain in the UAE, compared to here in West Virginia, we get around 40 inches of rain per year. It's only 10% of the total depth, but generally it happens all on the same weekend. You know, within just 1 or 2 days, you'll get that full 4 inches of rain, and when it falls onto rock, it concentrates quickly. So these are expensive culverts, which are really big. Sometimes culverts will be small and held together with old road signs. But it's important to know what the capacity is in order to prevent the sorts of failures that we saw earlier where piping occurs and sediment is carried away downstream. So HY8 is freely available. You don't have to have access to WMS. If you move on to an employer in the future that doesn't want to pay for WMS, you can get HY8 separately, although you had it installed as a process of the WMS installation. It is just free standalone software as well. So here's what we're going to do. Together we're going to go through breaking down a culvert problem, and screen by screen we're going to be entering in the details together. And so if you've got your computer, I'd suggest that you start up HY8. When you do, it'll prompt you to either open an existing project or to start a new project. And so start a new project and then make sure it says add a culvert crossing. Otherwise we'll have to do that manually. In one project file you can have multiple crossings, and for each crossing you can have multiple culvert barrels. So we're just going to do a single crossing and a single culvert barrel. But before we get too far into the program, let's just try and break down what we're looking at here in the image. I hope it's self-explanatory that this is a top view. What we're looking at is a road. That's the black thing with the yellow line in the middle. We're looking down from above at a road, and here's a stream. So the water, the blue stuff is water. And there's the geometry that we have to put into HY8 is we have to tell it how wide the stream is. And in particular, it's the downstream. So here the red is saying that the water's flowing this way. It's the tailwater that is most important for us to specify, because it's going to be calculating how deep is the water after the culvert. Because it wants to, if we go back to these diagrams from before, HY8 wants to try and determine, is the downstream pipe openly discharging to like the atmosphere, or is it fully submerged? So part of its assessing whether it's inlet or outlet control is it's going to calculate a tailwater rating curve. And so it's going to look at what flow rate yields which depth downstream. So we have to tell it like the end value of the downstream channel and the slope of the downstream channel, the width and the geometry. So, you know, is it a rectangular channel, trapezoidal, irregularly shaped, where we're going to put in some cross-sectional coordinates. So we're going to have to specify the downstream channel characteristics. We also have to tell it the crest length. And so let me try and help you visualize that if water is rising upstream, so if the water is rising and rising, it's going to get to a certain height where it flows over the top of the road. It's creatively described as overtopping, when the water goes over the top of the road. But it acts as a weir. It's acting as either a broad-crested weir or a sharp-crested weir, depending on how wide the road is. And so when it asks for the crest length, it's basically asking how long is the road from here to there when the water level has risen enough that it's about to flow over the top. So if it's a rectangular channel, the crest length is just the same as the width of the channel. But if you had a trapezoidal channel, which is probably more likely in most natural locations, then let's look at the culvert from the front. Then if we had a trapezoidal channel, and we're going to put like a culvert in, and here's a road on top of it. So we've got a road, like here's the asphalt. The crest length would be this distance. And it needs to know that because it's going to be doing some weir calculations to find out how well the water's flowing over the top of the road. So when the water level is rising and rising and rising, when it's this deep, water's only going through the culvert. And when it is this deep, the culvert's fully submerged, but the height of the water isn't yet to the crest. It's still only going through the culvert. But eventually, if the water level continues to rise further and further above the capacity of the culvert, some of the water is going to be going over the top, and some of it's going to be going through the culvert. And so HY8 will give us the breakdown of how much flow goes over the top versus how much is going through the culvert. So crest length is a really important parameter. It's also going to want to know the width of the road. And the width of the road has to do with its calculations related to overtopping. It's going to want to know what the road is made out of. Is it gravel? Is it asphalt? Because that too has an effect on how high the water level has to get for a certain amount of flow going over the top of that obstacle. Stations are going to be the way that we describe the crest length. And stations are also the way that we're going to describe how long the culvert is. Because we've just been looking at the culvert from the front. Here, and this is a side view of the culvert, this example that we're about to do. So here you can see that the culvert elevation is specified. So you can see the invert, meaning the bottom of the culvert here, has an elevation of 300 meters. The invert elevation of the outlet is 299. And so the slope of the culvert is defined by the difference in elevation and the difference in station. So the inlet station of the culvert is 100, the outlet is 20. And so the delta Z divided by the culvert length gives us the slope of the culvert. So in this case, the difference in elevation is 0.05 meters, and the length of the culvert is 20 meters. And so that's going to yield a slope of, let me get my calculator out here. We won't actually put in the slope directly, we're just going to put in these coordinates. But sometimes you'll know the slope of the river and you want the culvert to match it. And so you'll have to synthesize invert elevations. You won't be given the elevations, but you'll have to determine them so that it matches the slope you know that you want to match up to. I got a good question after class last week. That picture that I showed you of the culvert in Colorado, like why does it stick out so far? I don't really know, honestly. Maybe they were just trying to get the scouring water away from the soil. I don't know. Maybe they just didn't want to cut the culvert. It could be any number of things. But what you'll notice is that here, the culvert invert does not match the bottom of the channel. And for a lot of the analyses that we're going to do, we're going to assume that the culvert does match the invert, meaning the bottom of the culvert. It does match the bottom of the channel. So if we look at this side view here, what we're assuming is that the outlet of the culvert, the elevation of the outlet, matches the elevation of the channel downstream. Okay, so this example is asking for a design flow of 25 and a maximum flow of 30 cubic meters per second. Then is a 600 millimeter culvert going to be okay? Like, is that big enough for this flow rate? So let's see if we can get all of this put in. So here is HY8, create a new project, add a crossing. Okay. Okay, so crossing 1 is the default name, and if we look, the minimum flow rate that we want to, oh, well, we're in traditional units, so the first thing we're going to have to do is switch it over to SI. So cancel. Okay, here in US customary, we can switch it to SI. And my always go-to thing when I've had to change the units is restart the program. Because I've seen too many programs where it just is not successful unless you, oh, it's still in US customary. Culvert, new crossing. Okay, now it's in cubic meters per second. So I guess we don't restart, but set it to metric, and then you'll have to put in a new crossing with culvert, new crossing. Okay, so the minimum flow we're going to look at for this analysis is 0 cubic meters per second. Sometimes if we want to like zoom in and understand with more precision what's happening in a non-zero range, sometimes we'll set the minimum flow to more than 0. But let's just go 0 and then 25 for the design flow and 30 cubic meters per second for the maximum flow. So those are pretty high flow rates. Those are the flow rates you'd maybe see coming out of a 10 square mile watershed experiencing the 2-year storm. Large flow rates. Okay, now tailwater. We're having to characterize the channel downstream. So in this, it says it's a rectangular channel. So let's set the, okay, it's already by default on rectangular. You can see some of the other options are trapezoidal, triangular, and so on. Rectangular channel. The bottom width we're going to say is 5 meters because it's rectangular, and we can see from the top view that the width of the downstream channel is 5 meters. So the bottom width of 5 meters, channel slope 0.0025. That was given in the here. 0.0025 is the channel slope downstream. Manning's N, in the drawing it says it is, or here, 0.05. .05, and then channel invert elevation. Okay, so that's asking what is the elevation of this channel. You know, like we're using some common datum to describe the elevation of the roadway surface, the elevation of the invert of the culvert, the outlet invert, and here we're matching, we're saying that the stream has the same elevation as the invert of the outlet. So 299.95 is what I'm going to say for the channel invert. So 299.95. And if you click here on View Rating Curve, then what it'll do is it'll do a bunch of calculations for us to say at a certain flow rate, how high what is the depth of the water in the channel. So this is actually pretty interesting stuff. We can plot it here. And this shows us for a certain flow rate at what elevation is the water downstream. So this is important because what it's going to be doing is it's going to be telling us how deep is the water downstream, and it's part of what HY8 used to determine whether you've got inlet control and outlet control, and then once you know whether it's inlet or outlet, there's all these different equations that apply depending on what kind of flow characteristics exist inside the culvert. All right, so we have calculated the tailwater rating curve. Any questions so far? Now let's put in the roadway data. Roadway profile shape. It can be either constant, which is saying that the road's at the same elevation, which is what I've drawn here on the whiteboard. But there can be cases where you've got a culvert in a sag, like if the road was going down and then it went like this. So, you know, if the roadway profile was like that, then obviously as the water gets deeper, it's increasing the crest length. And so the options in here, irregular, if you wanted to define the shape of the sag, or a constant roadway elevation, which for simplicity's sake is what we're assuming. We're assuming that the roadway is constant and then the elevation is at 307 meters. Okay, so I'm going to say roadway elevation is constant. Crest length crest length is 5 meters because it's the same crest length as the channel width. So 5 meters for the crest length. The crest elevation is 307. That's the height of the roadway surface. 307. It's paved up the top, and then the top width. We'd need to know like how many lanes there are. Let's see, is there anything here that tells us specifically what's the width of the road? Okay, well, it looks like it's about the same as the culvert length, and the culvert itself is 20 meters. So let's just go with 20 meters as the length of the road. Okay, top width 20 meters. And this roadway station thing here, we don't really have to, that doesn't calculate anything. I guess maybe that is so that you could keep track of which culvert is which if you had multiple crossings. That's more descriptive than as an input parameter for calculating things, this first roadway station. Because if we look back at the sketch here, Like here, typically in roadway design, you'd have some sort of a control point set, and then everything along the road is measured in meters away from that control point. So we're saying that the culvert is at a certain roadway station, 3 plus 35. I guess we could put that in there. What was it? 5 plus 35. 535 for the first roadway station. Just to describe where the culvert is. All right, now the characteristics of the culvert is over here on this right screen. And our culvert is described to be circular concrete pipe with a conventional outlet. The invert's at 300, the outlet is at 299.95, and then the inlet station 1 plus 00, outlet station 1 plus 20. Okay, so those are the characteristics I'm going to put in here. Circular concrete, and what diameter did the problem statement say? Was it 600 millimeters? All right, so let's put in 600 millimeters as the diameter. Leave the embedment depth at 0. I'll tell you later about what that means. The Manning's N here of 0.012 is just, it's picked that based on the fact that we selected concrete. If you change to a different material like galvanized steel, then it would have a different N value. But you can overwrite it if you happen to know, for example, maybe it's broken concrete that's rough, and so you could adjust the N value appropriately. Okay, the culvert is straight. We're going to go with just these default options for the inlet characteristics. And so here where it says inlet configuration, square edge with head wall is the default. And you can see the K value that it's applying there is kind of like inlet energy loss coefficient. And so they could have a smaller inlet coefficient if it's beveled or if it's a grooved end projecting and so on. We'll just leave it with the default. And inlet depression is talking about if there was like a pool just before the culvert as a location for sediment to be trapped, then it reduces the capacity a little bit having that plunge pool immediately before the culvert, but let's just leave it on no. So the only thing we've specified really, we left it default circular concrete, put in 600 millimeters, and left everything else by default. Okay, inlet station. This is where we're going to tell it how long the culvert is. So inlet station 100, outlet station 120. So now we've told it the culvert is 20 meters long. Inlet elevation was 300. Outlet elevation was 299.95. So from that, it's now calculating the slope. It's calculating the slope based on the length, which we defined with the inlet and the outlet stations, and the elevation of both inverts, which was inlet elevation, outlet elevation. Okay, so now we can click on Analyze Crossing, and what it's got in the summary here is a table of how high the water elevation is going to get for a certain flow rate, how much of the water is going through the culvert, and how much water is going through overtopping. And so the question was asking us to analyze, is 600 millimeter culvert going to be okay? Like, can we accommodate 25 cubic meters per second through a 600 millimeter diameter culvert with no overtopping? So what's the answer? Can we? I see some people shaking their head no. Absolutely not. Like, to get 25 cubic meters per second through this area, only 1.5 is going through the culvert, and 23.45 cubic meters per second is going over the road. So this culvert is wildly undersized. Like, it's much, much too small if we're truly trying to get 25 cubic meters per second through there. So now we go into the design phase. Like, if we wanted to accommodate that much flow without any overtopping, how big would it need to be? Double click on culvert 1 again. By the way, it'll give you like a little sketch of where's the water elevation. So the water's up to the top in the barrel and then overtopping. So here's the water surface at 25 cubic meters per second. So only 1.5 is going through the culvert. The rest of it's going over the top. So double click on that. Let's try and make the barrel bigger. So we are, like, how big could it be? Like, how big of a culvert could we fit? Let's consider that, because there is a maximum limit that's feasible. Like, if it's 5 meters wide in the channel, then the culvert can't be any wider than 5,000 millimeters, because then it would be wider than the channel. Or if we look at the elevations, if the bottom of the invert's at 300 and the roadway's at 307, then vertically our limit would be 7 meters, or 7,000 millimeters. Of course, you'd want to have some cover. You couldn't have like people driving over the concrete of the culvert. Generally, there'd be at least 1 foot of cover, and for a culvert of that size, probably even more. Well, let's just say, what if we made the culvert 5,000 millimeters in diameter? So it's taking up the whole width of the channel and much of the available height. What would the flow situation look like if we go from 600 to 5,000 millimeters? So click OK. Actually, analyze crossing. Okay, so now what happens with 25 cubic meters per second? At 25 cubic meters per second, the water level is at 303.94. So the headwater can go as high as 307 prior to overtopping. So we're actually good with this gigantic 5-meter diameter culvert. In fact, what it's telling us is that when the water gets up to 307, when overtopping begins, you're getting 48 cubic meters per second through the culvert. So maybe what we've determined so far is 600 millimeters for what we want to do is too small. Too small. Because, like, what's the indicator that it's too small? There was overtopping, and we want this to have flow accommodated with no overtopping. 5,000 millimeters was too big. So let's just assume maybe that, like, the commercially available sizes go in 250 millimeter increments. I don't know that that's true, but let's just, like, let's take it down from 5,000 and try and nail it to what would maybe be more appropriate. So maybe as a first guess, I'd say, well, what about 3,000 millimeters? Analyze crossing. Okay, at 3,000, we still have 25 cubic meters per second, only going as high as 304.7 meters at the headwater. So we could still make it smaller. What about 2,000 millimeters? Analyze crossing. Okay, we're getting closer. So look at this, 307.03 at 25 cubic meters per second. So at 25 cubic meters per second, 19 of it is going through the culvert, 5 of it is over the roadway. So we need to make it a little bit bigger. So 2,000's too small. 2,500. Analyze. Okay. 25 cubic meters per second, no overtopping. So we can make it smaller. Unfortunately, there's no goal seek. At least I'm not aware of goal seek. You know, in the same way that rather than doing the repeated manual iteration in Excel, we would tell it what our criteria is. I don't think that that exists for HY8, but we just make it, I forgot, was it too big or was it too small? It was too big because we don't have, yeah, we can make it a little bit smaller maybe. So just like if it was in 250 millimeter increments, then what about 2250. Analyze crossing. So at 2250, we're still, okay, we're just barely starting to get overtopping. Because look, 307 is kind of our cutoff point. When the water levels rise to 307, then that's when it just starts to trickle over the roadway surface. And at 307, 24.92 is going through the culvert, and I guess 0.08 cubic meters per second is going over the road. So maybe we can convince our client that 2250 is just the perfect size, because we're going to just start to get like tablespoons of water over the roadway surface at that size. But if they say no, we don't want to have any overtopping, not even 0.08 cubic meters per second, then we'd have to jump it up to 2500. Okay, so that's kind of the design process when it comes to these culverts. You know, like you're given a threshold, the threshold being a certain amount of water that can go over the top, or a return period that's acceptable. So, you know, if they told you not the flow rates, but if they said, we want to convey the 2-year flow through the culvert with no overtopping, then what you'd do is you'd, for the location of interest, so for instance, like with this assignment, you'd go to the location, you'd put your outlet, you'd delineate the watershed, use NSS or HEC1 or TR55. You'd use a model to find out what's the runoff associated with that return period. And then with that flow rate, then you'd start building a culvert and looking at how high does the water level get for a certain diameter. And sometimes, in our case, it seems like the tailwater rating curve, when we get 25 cubic meters per second, then the water depth is at 3.8. So the tailwater, actually this is going to be both the inlet and the outlet are submerged. You know, because we kind of settled on the culvert size being 2.5 meters in diameter. So if the culvert is 2.5 meters in diameter, then what that's showing us is that it's fully submerged at the outlet. And so, you know, here we get that visual clue. This is the water level relative to the culvert location. Water level upstream, water level downstream. You can kind of see that this is at a slope. So any questions about this first example with HY8? I have a special affinity for HY8 because when I graduated with my master's degree, I was looking for a job. And it wasn't like now. You guys are entering the market at maybe the best time, like since the 1950s, to be a civil engineer. Honestly, there's more going on, more opportunity, higher salaries on a relative basis than since the end of World War II, practically. But like when I graduated and was entering the market, there was not a lot going on, and there were plenty of graduates and very few jobs. And so I was like really struggling to find places that had openings. But the place that did hire me, they hired me because I knew how to do HY8 a little bit, and nobody there knew how to do it even at all. So even just like a little bit of software familiarity can be sometimes the deciding factor on whether you get a position. So that's kind of like why I appreciate HY8. It's a lot simpler to use now than it was back then. When I was learning HY8, it didn't really even have a graphical interface. It was a DOS-based program in those days. Let's look at this next example. All right. So we've got a culvert where it's 1.5 meter by 1.5 meter. So it's not circular. It's a box culvert. Looks like it's made out of concrete, just based on this N value of 0.013. We know the slope of the culvert. We know its length. And we know the slope of the N value of the channel downstream. So the analysis that we'd want to do here is find out what flow rate will cause the headwater depth to be 2 meters. So, you know, what flow rate will cause headwater to be 2 meters where the channel width is 5 meters. So that channel width, I guess we're assuming here, is rectangular. Yeah, rectangular channel. And then what would be the width if we're going to move away from the 5 meter width? What would be the width that causes the tailwater depth to be 2 meters for the flow rate that we determined in Part A? We don't really have time to do this one, so here's what I'm going to suggest. I noticed some people don't have their computers today with HY8. Bring it on Wednesday, and we're going to spend all our time on Wednesday doing this example and the next one, just to kind of reinforce how to use HY8. In the meantime, I'd suggest that you go ahead and get started on this design project 1. It's worth a lot of points. You could start on the partial flume part of it, and maybe if you want to try and begin the analysis part as well. So I'll see you on Wednesday.